Welcome to my Commodore 64 Games Memories. This is where I look at old games and some of the technical details behind them. Let's get into it. Today we have Flying Shark, released in 1987, published by Firebird, copyright Taito because they did the original arcade version. The developer was Catalyst Coders, and the coder was Andrew Parton, the graphics by Andrew Threlfall, and the title screen by Paul Doherty, and musician was Jim Evans, apparently. So I remember this game from a cover tape, which made me want to get the full version because it was so good. It was very, very hard, but I had the UK version, and the UK version had this lovely vertical scrolling effect with the sprites down the right hand side doing the score panel. Anyway, so first of all, I want to have a look at what's on the disc and how it boots. Now bear in mind that this is probably going to be a very, very long video because I want to delve quite deeply into the protection for this disc version. I'm lucky enough to have the as close as possible to original G64 image, so I'm going to have a really good deep technical dive into this. My goal is to basically find the point where I can save all of the game data and then compress it, and then use the compressed version to then start playing the game without having to go through all of the loading screen. Now, I know that this is a multi-load game. I'm not going to hack all of the multi-code parts. I'm going to try and get the game working. Now this is interesting. There's 42 images, or 42 tracks inside the image, and there's 35 standard 1541 DOS tracks. So we have a few extra tracks. Now I know that this is a GMA 87 protected G64, so we're going to bear that in mind. But first of all, I want to have a look at the boot files. But I'm just checking here. There we go. There's the original G64, and we can see that with the original G64, and when I compare it to the G64 for a standard 1541 DOS formatted file, we can quite clearly see that the G64 for Flying Shark has a few extra entries compared to the standard DOS formatted G64 file from a very quick formatting session in Vice. So we know that there is extra data in there, and I want to have a look at the two files now, the two DOS files anyway that were included on the disk. There are many more files stored as basically raw track and sectors, of course, as you would normally expect in a game protected by GMA 87. Kind of like called, I think it's bleep load, because so many of the loaders used to bleep. But I don't recall if this version bleeps or not. I don't think it did. Anyway, so we can see that the first file was going to be this AS file. We can see that it loads at 02A7 by default. It's also got a standard basic header, so if you loaded it star, comma 8 instead of comma 8, comma 1, it would load the basic code, and then like the other protection files, or other files using this protection method rather, they would then very quickly load the desired file and then run that instead. But this is an auto-run file, or it was an auto-run file that we were just looking at, and it just basically looks like it's going to hop into 2A7. And then there's this file here. Here's the link for the GMA 87 protection. We know already now that it looks at track 38 and it looks for a signature of raw bytes. So we're going to see if we can look at these raw bytes, I think. What I want to do is that I want to go through the protection in detail for this. So we can see actually that there is an NTSC text string and a PAL text string as well. So this is the version that Graham was telling me about, where it probably detects between PAL and NTSC. Now that's the weird thing, is that there was an NTSC version, an American version of this for NTSC Commodore 64s, and it was done by a different team. It seemed to borrow quite a lot of the graphics and stuff, but the title music, actually it was full screen horizontal scroll, but it had a score panel, I think, up at the top of the screen. To be honest, I prefer the UK version. The US version lacks some of the finer details of animated water, for example, whereas the UK version has animated water graphics and things like that, which brings a lot more life. So I'm just having a look at, or just using my updated C1541 code here. So I've added some extra features which are missing from the standard C1541, which comes with the standard Vice distribution package. One of them is being able to read raw GCR data from extended tracks. So I can definitely see that there is data here. Obviously, it doesn't seem to be DOS format data. It's weirdly formatted data, as you would normally expect for protection information. So anyway, in anticipation of finding the drive, executing some code, I'm going to do the usual thing of loading some labels, and I've got my computer and my disk drive disassembly views open. There's that label file. Basically I extracted most of the Commodore 64 kernel labels, of course, like last time. If you've watched my previous videos, then this is one of my standard label files that I use when I'm debugging with Vice. It's got a whole bunch of breakpoints, which I don't really want at this particular point in time. What I want is that I want the standard kernel to actually start loading the game, but then I want it to hit a breakpoint that I want it to hit, which is going to be the first breakpoint going into the auto run file. Whoops. Let's try that again, shall we? Let's put a breakpoint in a place where I want it to be. So I'm expecting it to probably hit one of the vectors. We'll see what vector it is right now. So let's have a little look. And yes, what a surprise, it's using the 302 vector, which is a fairly standard vector for auto run code. And we can see from the disassembly it's doing a set message, set LFS, set nam, which is setting it with the name, for a file name with a length of 3 bytes, and it starts at 2C1. So we've got GM1, which was guess what, the second file, and it's loading that. It's setting the screen color, it's clearing the screen RAM, it's then doing a load, it alters the stop vector high. There's a few nops, probably just knopping out a few things which weren't needed in this release, and then it jumps to the code, which was just loaded at C000 in hex. Here we go, no surprises, very, very simple auto run. Things are going to get a lot more difficult later on, almost guarantee it. Bleep load is quite difficult. Anyway, so I'm not going to hack the multi-load. I'm going to try and compress the game data plus its first level loaded data, and then use that as a compressed version. So now I want to re-enable those breakpoints in the kernel functions, the C64 kernel functions. Now that the first load is finished and the second load of the real file is finished, I want to try breaking into the kernel functions. But these are the serial functions usually, so I can see what it is doing. Basically, I want to try and trap stuff that it's sending to the disk before it actually gets there. So we're just going to put some breakpoints in the disk as well, from 200 to 2000 in hex, just so that if we miss anything from the Commodore 64 side, then the 1541 disk drive will hit a breakpoint and it will execute some code. So here we go, straight away, a serial bus send data in the kernel from the Commodore 64. Not a surprise. 4D and 2D going to the char out routine. Almost certainly, if I remember correctly, that's going to be an M command with a dash or a hyphen after it, and then it is going to send either W for memory write or E for memory execute. Of course, it's one of the standard ways of sending serial data to the 1541. So far I haven't found kernel compatible serial routines sending data using code that the game creators have used that sends compatible kernel serial data but in a smaller package. I haven't found that yet. It would make it harder to reverse engineer what it's trying to do rather than using standard kernel functions. But based on my experience, this GMA87 protection method, it tends to send code to the drive quite quickly and then starts using a 2-bit protocol to send and receive data to and from the drive, which is a faster way of doing it, and it's also an obfuscated way. But the thing is that often with this protection code, it seems to reinitialize the drive by using again the kernel routine from the Commodore 64 to send serial information using the standard kernel serial bus entry point. So the benefits that this protection got from using its own 2-bit protocol were then a little bit negated by having to drop back and then use the kernel serial bus calls again. I'm not entirely sure why it was sending practically the same code over and over and over again to the drive when it could have just had the code in drive once. Actually, it could have loaded that from a disk sector rather than sending it from the Commodore 64. Even that would have been a little bit more efficient, but hey ho, such is life. You just send a command from the Commodore 64 saying execute code from this disk sector. That would have been a lot harder. Anyway, we can see here that it's doing a m-w command. No surprise there. We will hop back out now and get back to the code that it was actually running. We'll have to do this a few times because the kernel gets quite deep into its own functions, and there are some breakpoints there as well that we want to get out of. So there we go, we're back out now. So some of these kind of protection routines that are trying to send data to the drive, they sometimes jump quite early into send data deferred, which is a different way of doing it rather than having to do the setlfs and set and open and stuff like that, which is an interesting way of doing it. Or it starts using half the load routine in the kernel and then it starts squirting out its own custom data, which is also a good way of doing it, but it's still using the standard kernel serial routines, which, there are pros and cons. Smaller code, easier to use, and it will work, compared to easier to reverse engineer and to try and trap out what's going on. That does a little bit of a delay loop with a good chunk of NOPs there. There is a delay loop in the kernel. I don't know why they weren't calling that one. Whatever. So this is now going to cint the screen editor, the standard kernel print routine and screen initialization, if I remember correctly. So this is doing a check with 2A6, which is the video system, the machine type, if you like, the region, NTSC or PAL, and it seems to be copying the string NTSC, is it? No, it's copying the string PAL over the string NTSC or vice versa. Anyway, yes, basically it's checking the TV standard and then doing the necessary copy. It's setting up a pointer into the RS-232 output buffer at FA and FB, so it's indirected with FA and FB. There's a little char out routine there. Well, that's doing C433. C433 is the The system NTSC or PAL GMA87 loading fly shark. It's using the standard kernel print. Well, that's why it's using cint then to initialize the standard kernel screen display routines. Interesting. So it's using PETSCII character codes, right? Because it's using char out. To be honest, I used to use those routines as well. For some things, I think I used it for like a music demo or something like that. Way back in the day. So this is not part of the protection, I'm just quite intrigued. If I remember rightly, there is actually a kernel entry call that you can use. Instead of char out, you can use string print, isn't there? Where you give it the X and Y registers, I think it is, for the low and high address, into the memory with a null terminated PETSCII string, and then it will actually print it for you. So I don't know why really it's doing this reading and then sending, where it could just set up the address and then tell the kernel to print all of the messages that you want it to print. I mean, you can tell it to clear the screen, you can change colours, you can change the character set, I think. You can reverse on, reverse off, you can do all sorts of things. You can move the cursor around, up and down, left and right, all sorts of things. So it would have definitely been more efficient to I think use the kernel string print routine, which prints everything out in one go. It does need more of the 0 page to be initialized correctly, but you're coming from BASIC. So BASIC, having loaded the file and running it, it should have been, well, okay, so the auto run method may disturb some of the 0 page addresses, but that's the whole purpose of using the JSR2C int that we saw earlier on in the code, right? Anyway, it's sending more serial bus information now after doing the screen print that we can see now. That it's saying system PAL, it's got the GMA87 text up in the top right hand corner, and then across the middle of the screen roughly it says loading flying shark. It should be shark, but it just hasn't refreshed that screen yet. Anyway, so M- more chart outs coming now, but this is for serial bus sending. DD57. Anyone know what 57? Does anyone remember what 57 is? M-W. Of course, it then sends, the low and high address of where to start writing to and the number of bytes that you want to write as well. Of course, this is all standard M-W memory write command code. Very, very, very standard serial bus stuff. This is not at all surprising at the moment. Where it's going to get really interesting, and you need to be very awake for and have lots of coffee or tea, is when the code starts running on the drive. That's going to get rather interesting. So $43 in 0 page is the low byte offset of where to start storing code to in drive memory. So it's currently at 0, so it's storing at $ in hex 300 in the drive's memory. It is going to start reading that code at C0CB, of course. So an interesting feature of the drive, which many people don't remember very often because it's not very well documented, is that the overflow flag for the processor status for the CPU 6502 in the 154 on disk drive, is that the overflow flag is actually wired to the drive hardware finishing reading a byte of raw data from the disk. This is not a byte that you would send to the Commodore 64. As such, it's usually a byte that you would decode because it's raw data coming from the disk, and the raw data from the disk is usually GCR encoded, and that's because, without getting into too much detail, data on the disk head reads magnetic flux changes, and it's not terribly reliable at reading too many bits of zero value, for example, one after each other, so that the coding on the disk for data has to avoid too many sequential bits. So this is the whole point of GCR encoding for data, is that it expands the data, so 4 bits become 5 bits, for example, but the 4 bits, when they are encoded, they avoid having too many repeating bits being stored on the disk. Anyway, so the whole point of GCR encoding is to avoid the hardware limitations of the read head on the drive hardware. So anyway, we're getting to that point now where it has sent over a whole bunch of data to the drive, and it looks like it's going to start trying to execute that code on the drive. So we'll put those breakpoints back into the drive side of things, just so that we can trap out exactly when the drive starts executing. We are going to get to that point really soon. That's where the fun really starts, with the GMA protection. So I'm pretty sure, almost 100% sure, that the code in the drive will start running at 3v6, but just to be on the safe side, we'll put a range breakpoint in there. Because you look at what it's trying to send from the Commodore 64 for a memory execute. So here we can see that this is actually the code on the Commodore 64 side for the 2-bit protocol read, by the looks of it, because it's doing a load. We can see down at C1DF it's doing the 4 chunks of read code, and there are actually 2 of them. There's one at C1DF and then there's one at C1FC, and they are subtly different. We can see some subtle differences there, which to me indicates that perhaps it's tailoring the code to NTSC or PAL. That would certainly make sense. The timing would be different, you see, for NTSC and PAL, very, very slightly. Anyway, so this is actually doing the same kind of thing. It's looking for, for starters, it's using the 0 page, 43 and 44 in hex, $43 and $44 C19D and C1D0, you can see there. It's using the 0 page to send or to store those pre-calculated serial bus values from the Commodore 64 side, but then it's doing a raster position check for the screen to avoid those bad lines. This is what we've seen before with this fast load, and now we can see that it's actually starting to run the code as we expected from inspection. It's starting to run the code at 3b6, and straight away it tries to do a load BAM in the drive code, which is at D042 in JSR to D042, and then after it's finishing reading the BAM, the block allocation map, basically, it reads the block allocation map and it stores it in one of the internal buffers. It reads it, decodes it, stores it. Often the block allocation map would contain data or code. It's a good, cheap, quick way of getting the data that you want from the disk into a known place inside the disk, inside the 1541's memory, one of the internal buffers. Now, what this is doing is that it is, sometimes I despair at this disassembly view. There we go. So it's 1632 $33 $21 in hex is 33 in decimal, and it's reading track 33 sector 2, and we know that because we've got the 1541 job code. Since it's using the 1541 job code interface, that means that the interrupts are going to have to be enabled at some point in the drive code, and then a timer interrupt will come along and then service those job codes. Okay, so we know at the moment that it's still using the 1541 ROM routines. You can see that it's storing it into 0 and then loading it with 0 and then branching on minus back to 3C5, which means that it stores the job code E0, which is read and execute, but also move the heads to that position. Okay, and then execute the code. And what it does is that it starts executing the code at 300 in hex in the drive memory, and we know that there is code at 300 in hex in the drive memory because that's the code that's in the buffer. And then it loads from 0, which is loading the job code, and it's testing it if it's minus. If it's still minus, it hasn't finished the job. If it's plus, then it means that it's completed the job. Okay, so it's moved the head and it's executed the code at 300. This is quite a good obfuscated way in the drive side of things to actually execute code without looking like it's executing code. Quite a cool way of doing it, I suppose. If you don't know that command E0 does, execute code at 300. We're going to put a breakpoint. Well, actually, I'm thinking that we should really put a ranged breakpoint. I mean, based on acquired knowledge, yes, I know that the drive will execute code at the beginning of 300 in hex, which is the beginning of its buffer in RAM. But to really test this, just to really double, triple, quadruple, make sure that the drive code is behaving as we would normally expect, I think we should probably put a ranged break in. It would be a good idea. Notice that the track and sector 33.2 in the disk image is correctly formatted DOS sector, so C1541 is still able to read and decode the GCR data to normal bytes that you would normally expect to see. Okay. The interesting thing here is that it's if you have a look at the second and third bytes in the sector dump there, it's got 00C8. Swapping those around, it's C800, which is inside the Commodore 64's address space. So it looks like it's going to be sending this data back to the Commodore 64. And the Commodore 64, it looks like it's trying to load a file, right? Because 210C is a good sector interleave value. So it was originally reading sector in a track and sector 33.2, which is 21 and 2 in hex. And now it's reading, or it looks like it's a sector chain, track and sector chain. So track 21, which is 33 in decimal, and C, which is a good interleave value for standard DOS files for track and sector chaining. So blocks, when they are DOS formatted blocks, the first 2 bytes are a track and sector offset. If the track is 0, it then means that the sector size for the last sector has been reached. And then it goes off through a chain of the first 2 bytes of every single block being the track and sector, next track and sector to read. If the track is not 0, then that means go to that track and then read that sector. And that means that the rest of the data, so 256 minus 2 is 254 bytes. The rest of that data, 254 bytes, gets used as a full sector, and that's the full data for the file until it goes to the next sector in the chain. Okay. So it looks like the Commodore 64 is going to be receiving that data and it looks like it's going to be receiving a file which is at least 254 bytes long, longer actually, because the track is not 0. Okay. So the hardware vectors for the IRQ in the drive is basically here, and then the interrupt routine gets called on the drive, and the interrupt routine is based on the timer. So there's no interrupt from the serial bus usually, hopefully, when it's looking to service the drop codes, and then it goes, is it from the timer 1? If it's not from timer 1, then it hops over it, but if it is from timer 1, then it runs the job code servicing routine. Okay. So we'll put a breakpoint in the drive at FE67, and we'll put, I think we should really put a range breakpoint. So to make sure that we're not going to get caught out and execute some unexpected code, we're going to put a range breakpoint for 300 up until what, just before this code really, so 3B8, right? And then we'll put another breakpoint from just after that code as well. That would be a sensible thing to do. Not this time, I don't think. Anyway, so it's starting to go into the routine for servicing the job codes. Now, the routine for servicing the job codes, right, is at F2B0, right? So this drive disassemble, well, the C64 kernel and also the drive's ROM routine disassembly web pages are very valuable, fantastic work by whoever created them originally. The credit is actually in that file, right? So yeah, I've put them in my C64 docs repository on GitHub, and I've put a whole bunch of extra, I've accumulated lots of documentation over the years. Anyway, so it's all on GitHub, so everyone else can easily access it. It's also like a backup in case the website that was provided them goes down, which sometimes they do. I've been caught out by that before. Anyway, so we can see that the job code processing code is running through its thing. There are 5 or 6 different job codes, up to 5 job codes being serviced, I think, by the drive job code queue. There are slots, right? 3 bytes each. First is the job code, the second byte is the track, and the third byte is the sector. And there are triples of those going all the way down through memory, starting at 0 in hex. There is no processor port on the CPU used inside the 1541, which is just as well. So without the processor port and without the processor port's data direction register, which in the Commodore 64 are at 0 and 1, it means that the underlying RAM is accessible. So actually the 1541 has 2 bytes of extra 0 page addresses that can be used. Fantastic, right? Whole 2 bytes. So I'm just looking through this again from the drive disassembly point of view, just to familiarize myself with what it's doing. But to be honest, it's probably not a great idea to delve too deeply into the drive's ROM routines. We know what they do, they're very well documented. So we can see, as expected, that the drive has moved its head to track 33, and the code at 300 in hex on the drive has started executing, which is what job code E0 tells us to do. It tells the drive to do, rather. Now, I can see straight away the drive code at 300. What does this do? It changes the buffer address pointer that's being used, that's actively being used. So even though we're using the first job code slot, which is 0, 1 and 2, which should use, I think, this buffer, right? Buffer 300. It's changing the buffer that's going to be used to the buffer at 600, which is perfectly fine. It's a good way of putting the data without corrupting the code that you're trying to run. And then what it does is that it finds the start of the data block. Read the block header and wait for sync. The label names for the drive side of the code, for the drive disassembly, are not correct. They're the Commodore 64 label names. So anyway, it's looking for the track and sector. So the drive is spinning around, or the disk is spinning around. The drive doesn't spin around. No. The disk spins around, and it looks like it's looking for that particular track and sector that we want to target, which is 2102, which is in decimal track 33, sector 2, as you would expect it. And it looks like it does that by looking for block headers. It looks a sync in GCR formatted track and sectors is a whole bunch of ones, right? If I remember rightly, up to 10 bits, 15 bits of ones, something like that. And then it looks for the header data, something like that. Anyway, the header data is a few short bytes, so it's able to read that in and then decode it quite quickly to see if we're on the right header. So sectors are separated by headers and sync markers and the data again. So we have a header, sync, header, sync, data, blah, blah, blah. And it goes off through regularly DOS formatted disks like that, if I remember correctly. So anyway, the drive ROM code looks for these patterns of sync, headers, sync and data markers, so that we know that then we're at the start. We can then start saying that we want to start reading data bytes from the head, please, and then it will start sending I've read a completed data byte at the head and here it is type thing. Now the code has to be really very short and optimal, and remember that these data bytes are raw data bytes, so they're going to be raw GCR data because they're formatted track and sectors, DOS formatted track and sectors, and the code has to be extremely small and extremely tight, and it's quite time sensitive in terms of if you make your code too slow, it's going to miss bytes as the disk is spinning. As the disk spins around, it generates flux, which then is interpreted as raw byte data, GCR encoded, usually being interpreted by the drive head. So we can see once we hop out of this on the drive side of things, we get back to the code and we should start reading this data. Well, no, we won't. We'll read the raw data first and then we'll have to GCR decode it to then send it back to the Commodore 64. At the moment, it's trying to get to the right position as the disk is spinning around for the drive head. So yeah, very time sensitive. You'll notice at the moment that the interrupts are disabled. The interrupts are disabled because it's trying to read data. Right, so we're not going to have to wait that long for the byte to arrive. Okay, remember, the overflow flag is set when the drive head finishes reading a byte, raw data bytes from the disk. We won't have to wait that long because the disk is spinning. Now, because we know what we're looking for, we can compare for the expected GCR data coming from the drive head, which is loading accumulator with 1C01, which is a byte coming from the drive head. We're comparing it with what we expect. If it is not equal, then we know that it's not the right header, and then we go back and then we try and read again until we get the right header. The correct header, sorry. Read and write is going to be a confusing terminology to use. Correct. It would be correct. So this is just standard ROM, disk ROM routines for the 1541. There's nothing unexpected about this because it's the ROM routines. But it's good to have a look through them, right? Because it's good to understand at a low level exactly all of the work that the ROM routines are putting in, and they do put in a lot of work. But it's all quite understandable once you realize that you have a magnetic medium spinning underneath your drive head, or on top of your drive head, depending on your orientation of the drive mechanism. Anyway, so we get back at this particular point in time. We are waiting if overflow is clear. We're waiting for the next byte to come along. So the header and the sync has been reached at this particular point in the code. So we start reading bytes. Now these are raw bytes, as I say, usually GCR encoded, but not always. Some disks have their own format on certain tracks and sectors, which is perfectly fine and valid. As long as you know how to decode that custom format, then it's great. Anyway, so the data is then stored into a few different places. So it stores what looked like 256 bytes into the buffer at 600, and then it stores the remaining bytes, because even if a sector is 256 bytes long, when it is GCR encoded, it's going to be longer, so you need to store this raw encoded data somewhere else. So we need to store it in a different page, and it seems to use the start of the stack in the 1541 ROM routines, which again is perfectly fine and valid. So let's double check that the bytes that we've read in on the drive memory at 600 is 55 E4 B5. We can see it there, E4 B5 35 55 E4 B5 35. So we can see, using the GCR peek command in C1541 utility, that the raw GCR bytes that it reads are the same as the raw GCR encoded bytes. Currently in the drive's memory, sitting at the buffer at 600 in hex inside the drive memory on the left hand side there. So we know that we're reading this data from the disk and we're storing it into the drive's memory. But anyway, we need to read the next few bytes. Actually the next BA, so BB in total, right? Bytes, and storing them in the processor stack at 100 in hex in the drive's memory. So it's at the beginning of the processor stack, not the end. The drive ROM routines don't use enough of the stack space to grow down from the top of the stack into the GCR data, so that's okay. We can see it's doing the same kind of thing. Branch and overflow clear in its little loop, and then clearing overflow, and then storing the data, blah blah blah. F8E0 in drive is, of course, decode some GCR bytes, and that decodes it using the memory block there, which is of course the buffer at 600. And then once it's finished doing the decode, we can see in the Commodore 64, the drive memory at 600, that it's 210C00C820AE blah blah blah, which is the same data that we get from the bpeek command in C1541, so we know that it's decoding this data correctly. Which is all very cool, right? So I think this is double checking to make sure that the sector that's loaded is the one that we expect. F5E9. So yes, F5E9 is, oh yes, calculating the parity. So there's some parity information, which is basically like, well, it's a parity check. It's like a checksum for bits, basically, just to make sure the data is read correctly, and then it does a parity check, and if it's not correct, it goes back and tries to read it again. I'm guessing that would be the sensible thing to do. Yeah, it does look at F9690304 going back again to the code. Anyway, oh look, it's setting up the next. Well, first of all, it's reading the sector. So yeah, it's priming the sector to read next. It is then initializing Y with 2. Because the GCR data has been decoded now, so we know what the bytes are, so it's setting up the sector to read next, if there is one. It is then starting to read the decoded bytes from the buffer, and if it's not 1, it just sends them. If it's 1, it sends 2 of them, I think, because it's using a control code as an escape code, or it's using an escape character or escape value, in this case 1, as a control code. So hopefully 1 doesn't appear too many times in the data, because it would send twice as much data, but generally speaking it shouldn't. Statistically speaking, it's 1 in 256, right, if it's random data. Anyway, so it's using 1 as a control code. So it escapes that and it sends it. So it does this byte sending routine twice. You can see here, look, bit, BPL, bit, TXA, LSR, NSR, store, ASL, and store. So it's doing the 2-bit protocol to send the information back to the Commodore 64 from the drive, and it's doing that for all of the decoded bytes, plus control code escaping. The Commodore 64 will be using its 2-bit protocol reading code to then decode these 2 bits of data coming from the drive using basically the fast loader. Okay, we can see already that as the drive is sending data, the Commodore 64 side of the code was receiving the data, and this is what we would normally expect, because of course the Commodore 64 needs to be listening as the drive is sending its stuff. Remember, the Commodore 64 side does a little handshake and wait, and then a handshake with the drive, just to make sure that it's all in sync with the drive when it's processing these 2-bit data protocol chunks of data coming back from the drive. That is extremely time sensitive. But the initial protocol sending, I'm ready to say, I'm ready to send, and the drive sending back, yes, I'm ready to send, I'm ready to receive, the Commodore 64 says, and the drive says, yes, I'm ready to send, and the C64 says, okay, then send, and the drive goes, here it is, blah. Right? That's what happens, but the handshaking stuff is not time sensitive. It's only the 2-bit protocol transfer which is time sensitive. That's why it looks for bad lines in the raster position with the screen on, because bad lines soak up extra time from the CPU, and it freezes the CPU, it halts it, pauses it at that particular point in time. So anyway, the drive code sends all of this data, blah, 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 and the C64 receives all of this data. There hasn't been any protection check yet. By the way, the protection check will be later on, because we are, almost certain with the documentation of the GMA 87, was it, protection methodology, it's looking for specific raw bytes on the disk on a particular track, which is what track? We're higher up track, 38 or something like that. Anyway, so we haven't got to that point yet. We haven't seen anything which seeks to track 38, right? So anyway, the Commodore 64 is dutifully doing its receiving. The Commodore 64 starting to store data. We get a C8 on the Commodore 64. You can see it in the accumulator right now, and C8 is the high address byte of where to start storing We can see actually on the Commodore 64 code that it's doing a JSR with C19D. C19D looks like it's the receive byte routine, right? I think it was. It's basically comparing everything with 1, which is the escape code. If we don't get the escape code, then we know that it's a real byte, and it stores it in AEAF as an indirected address there at C2. Good memory address actually, right? C2 is the store of data. Indirected store with AEAF, comma Y. In brackets, in parentheses there. You know, I would have done the escape code decoding logic actually in the get byte routine itself. If the error escape code is sent or received, rather, I would have just pulled off the last 2 bytes from the stack and then returned to the routine previous. But anyway, this is doing it like that. It's doing a comparison with 1 for every byte it's receiving, just to make sure that it's not escaped, which I guess is fine too. Certainly one way of doing it. But it does mean that you have to do a compare with 1 every single time. Anyway, so the drive side of the code is still merrily doing its thing. It's still sending bytes. Of course, it hasn't finished sending all the bytes. The Commodore 64 is merrily still doing its receive buffer logic, as you would expect. There's the handshake again, the C19F there. So for the benefit of everyone reading the subtitles, just to confirm, it sends the DOS formatted sector back to the C64 using a 2-bit protocol. Nothing really too unusual. Nice drive code, but not unusual drive code, not really. So the code at 3B2 in the drive memory there on the right hand side looks like it's the Commodore 64 code. We can kind of ignore that, it's just floating around from what was read previously. Okay, this is one of the buffers that would have been used for a DOS file load, so it's just floating around from the previous DOS file load, I think. Or maybe it's just sending what was in the C64's memory back to the drive. Either way, it can be practically safely ignored. We're going to put a ranged breakpoint just to be on the safe side that the Commodore 64 code run will get trapped properly. I'm pretty sure about. That's on the drive side. I think it's still sending bytes. Commodore 64 is still. So that's just updating the job code in the drive drop code maintenance routine. It's just basically saying I finished the job. This is the job code processing code, again in the drive standard ROM stuff. The Commodore 64 is finishing off its serial bus code. It's also doing a delay for 1 millisecond there on the Commodore 64 side of things, and just to give the serial devices enough time to respond. On the drive side of things now, we're going to put another range breakpoint so that we can trap into the next execution of the job code framework, which then, or rather any command from the Commodore 64 which says run some code. We're going to put a breakpoint there in the drive side of things because the Commodore 64 sent something, usually. So that's interesting. 2048 is read block. Read block seems to read. Oh yeah, read the block that was set up. Okay, so that's the next track and sector that is wanting to be loaded, right? Which was the one that the drive loaded with just now from the previous track and sector. So let's put a ranged breakpoint in the drive code again, so we know that we will trap out the code when we return from the drive's ROM routine. Meanwhile, we have the Commodore 64 breaking on its breakpoint, which is the kernel init IO. It then jumps to a subroutine, which is at C800, which was the code that was just loaded from the drive, but loaded from the drive using its 2-bit protocol. So we're going to put some breakpoints on the char out, having a little look at 68EF, which is called from C813 in the Commodore 64 side of things. It's doing setnam setfs and doing an open which will then enable the code to start sending bytes to the drive again, so the drive is going to be waiting around for stuff. So looks like it's sending a memory execute command with 0397, which is at C85E onwards on the Commodore 64 side of things. The number of times I've read checkout as char out is quite funny. It's the same 6-letter label name, and it looks quite similar in this font. Memory write does a lot of memory writes. Again, FBFC is pointing to 300 in hex, but in the drive memory, because we're sending drive commands to the drive. So if we have a look at the code at CABF, we can see that it's doing a load and stores to 1C00, which is obviously drive code. 1C01, obviously drive code again, but reading a byte of the raw data from the drive's head. So the Commodore 64 is sending more drive code. After doing that initial drive code, which sent back the 2-bit data, it's now doing more drive code. Excuse me. So this time it's reading hex, $26 track, and sector 1. In the drive code it's at 397 in memory. Now 26 in hex is, as we've just seen, is 38 excuse me, in decimal. So this turns on the drive's LED, but it also clears the interrupt flag, so interrupts are now enabled. So it's like a dual purpose routine, and that's useful because here we can see it is doing the whole job code thing again, where it's going to move the heads, and then it's going to execute code in the buffer at 300 in the drive. We know that that's what it does. I'm just going to put some ranged breakpoints just so that we can really double check that the drive is not going to be executing any hidden code. For example, if there's any obfuscation that we've missed, we can see that it's reading the job code, testing for it being minus, and if it is, then it hasn't completed the job yet. So again, without too much surprise, we can see that the drive code has started executing its code at 300 in hex again. On the right hand side, we can see that the range breakpoint has hit. We can see in the Vice emulation display that the track is now 38. The sector is shown as 0. I think that might be because the track is not GCR encoded, so it doesn't actually really know what sector it's on. I think the sector that was set up for the drive is probably ignored. I think it just seeks the head at this particular point in time when it runs job code E0. You know, I should really create a label file for some of these common drive routines, shouldn't I? So that we don't have to keep on going back and checking that F969 is one or the other thing, but that's okay. Load Y, decrement Y, branch on not equal, so it's always going to branch. It's 312. So it's still running the code as part of this job, you see. So it's quite a useful way to get the drive to execute other code without making it look like you're executing code. The Commodore 64 is doing its 2-bit protocol raster check to avoid bad lines. Again, C1DF, we can see the definite obvious case of the 2-bit protocol receiving data from the drive. So 38 is the protection track. So this looks like it's a protection check. We can use the IO command in the Vice monitor debugger to look at the bits in 1C00 before and after, and it changes the bits at in the first register, in the 0 register, from DE to 9E. So from the upper nibble, the first and last bits are still set. It's not doing a head step because although this register does handle head stepping, it also handles the bit rate, the speed of bits that are being read or written to from the head. And it's changing the bit rate here. It's basically clearing bits 6 and 7, the upper middle 2 bits of the upper nibble. We can see that quite clearly in this before and after snapshot of the IO state of 1C00. We can see it's definitely changing the middle 2 bits from 10 to 00. So it's changing it to a lower bits per second rate. It then sets up the Y register with a value, decrementing it, doing a branch not equal, and it gets straight to this bit test here. Bit test for the upper bit of register 1C00 is sync detected. If sync is not detected, then it will be minus value because the upper bit, the last bit, the most significant one, is set, so it becomes a negative number in 2's complement register values. So 0 means sync found, so 1 means sync not found yet. So that's what we're doing with there we go, it's just looking for a sync, and then we'll wait a little while for the disk to spin around to a sync mark, and then we start reading bytes from the head, the raw data bytes coming from the disk arriving at the head. Now this code then looks for its signature that it's looking for in the data bytes that it's reading into memory, and it's looking for the signature where we have 69, 3 bytes that we don't care about, and then looking for A9. We know that the sectors in the track are not GCR encoded, at least not with correct header markers, so the normal bpeek command won't find them. The string of values that we can see in the drive memory here on the left hand side at 500, which is where it was storing the raw data bytes from the disk, it's not matching, but the signature check here is at 329 on the drive disassembly in the memory here, where it does compare with A9. It then loads 0504 in hex and compares it with hex 69. Don't forget that the bytes read from the drive are being stored backwards in memory at 500 in hex. Of course, because the DEX, the TEX instruction at 326 does it backwards. So I think what we can do is that we can put a breakpoint here so that we have a breakpoint after the drive code finds the correct marker it's looking for in the raw bytes coming from the drive. Don't forget the disk is spinning as I'm writing here, right? The bytes may or may not be GCR encoded at this point. To be honest, it's just reading data from the disk, wanting it to be correct. If it doesn't find it, it actually has this retry value, which is the Y register, I think. It goes back to 30A, you see, in the drive code at 332. If it's not equal, and at 32B, obviously it goes back to 30A, which does the decrement y and branch not equal. If it doesn't find the protection track expected bytes, looking for its particular signature, then eventually it will go to 30D in the drive code, which goes to jump to F969, which F969 returns from the job, and it looks like it's returning an error code from the job execution. Right, so the Commodore 64 will get a wrong value. The job of this protection code is basically to return a value to the Commodore 64 to say, hey, this is a real proper disk as opposed to a disk which has been copied. Okay, that's the purpose of this protection check. Now, the protection check is not specifically looking for this signature and then just returning. It's actually doing some extra checks down below, which we'll get to. I mean, the documentation for this protection scheme says that it starts doing some measurement of sync pulses and stuff like that. So if we have a look for the data bytes that it has found, we can see that the data bytes occur straight after a sync pulse, which are those 3 FF values that you can see at 860 in the raw data bytes from the disk, and then it's found that signature. Once it has found the signature, it gets into the second part of the protection check. So again, it's looking for a sync pulse. It's initialized the Y and X registers at this particular point in time. What it's doing is that then it is using the X register to time the number of X increments until it gets the next sync pulse. And then it stores that value again into the memory at 500 in hex, but indexed with Y. So it uses the X register to time sync pulses, and it does that for Y register times until Y register equals A at 348 here, which means that it measures say up to 10 sync pulses. It measures the time 10 times between sync pulses, basically. It then discards the first couple of measurements in this table. It then performs this compare, rotate left, load sequence of calculations to perform a calculation on the measurements of the sync pulse lengths. Now, the drive CPU runs at the same speed, regardless of whether or not it is PAL or NTSC. The only wobble factor here, literally a wobble factor, is the speed of the disk as it is spinning around. Hopefully the speed of the disk as it's spinning around doesn't vary that much, otherwise this protection check would fail. If you have a slow drive or a fast drive, then it will fail. But basically this protection check, once it has calculated a value based on those sync pulse timings, it then does the 2-bit protocol handshake with the Commodore 64, and it sends this information to the Commodore 64, and it is going to send the value that is in the X register. It sends the value in memory, in the drive's memory, at 50A and hex as well, which, as we can see in the disassembly, in the memory view there in the monitor, it's 61. So we are expecting to send the value 61, which is also in the X register in the drive's CPU currently. Won't stay there for very long, but it will stay there for a while. It's also 61. So the Commodore 64 should get 61. And of course, because the Commodore 64 is looking to receive that information, we hope that this information is used somewhere else, because then that will tell us pretty much conclusively that this is certainly a protection check. It might not be the only one, but it's certainly a protection check. So I've got a breakpoint at C1F7 on the Commodore 64 side of things. We can see that the drive code goes to F969. So the drive code, after it does the protection check, finishes the job. The Commodore 64 receives this information. We'll just continue on here. We won't bother stepping for all of the instructions. We can see that the Commodore 64 has received the value 61 into the accumulator register. We can see that in the register view for the computer, the first register view, the register view on the left, well, it was 61, no it's not. The drive has now gone into its job completion code, and then the drive has eventually, it goes back to the code which completes or tests for the job completion code being completed. It looks for 2 or 1 being returned by the protection check as well in the drive code. If it returns 1 for a good protection check, and it just does an RTS. So with the drive sending that 61 value that it read from, that it calculated from the timed sync pulses, we'll see what the Commodore 64 does with it, and it does this, it returns it at C1 F7 with that RTS. We can see it pulls the processor flag and it does an RTS. Now, pulling the processor flag seems to allow the interrupts to occur, which may or may not have been deliberate, but it's certainly a piece of obfuscation. It's a little bit sneaky. It makes it less obvious that you are enabling the interrupts, because CLI is a very obvious instruction, PLP is a less obvious instruction. So I'm pretty sure that at this stage it's doing the standard kernel interrupt handler. I'm kind of sure that there's nothing obfuscated going on here. It looks like it's just doing standard IRQ processing in the kernel. If I was going to be writing this, I might have made it a little bit more nasty and claimed one of the vectors, like the stop key vector or something like that. Anyway, at this memory address here, it's C073 on Commodore 64. It does a push onto the stack of the protection value, which the protection value is the code value that was calculated from the timed sync pulses, and it stores that on the stack, and it's going to use that later on. You would hope that it's going to use that later on because it's storing it on the stack. So at this point it's just doing a whole bunch of loads of data by the looks of it. So it looks like it's saying, I want to load this file, this file, this file, this file, because it looks like it's just basically going through a file table, loading different bits of data. During this load, it loads the title screen, it then loads the game data. Eventually it gets all the way down to here where it does a clear channel, or close all, sorry, I think it's close all and clear channels. And then a look at C3C3, it does a PLA, which is pulling the value from the stack. That's what it looks like. So let's see what it does when we continue on. And yeah, it's just loading data at this particular point in time. There we go. I'm pretty sure that it's just loading data. I don't see any other protection track checks going on here at this particular point in time. From a protection point of view, actually, There's quite a lot of free memory available. It's not checking for memory integrity or anything, as far as I could tell when I was looking through this code. So when it gets to C3, well, okay, so this particular piece of code at C3B2 here, you can see that it's actually restoring the IRQ service routine table from the vectors here, the vectors table in kernel, which is kind of cool. Nice way of doing it. And then there we go, it's read the calculated value, the magic value, protection value from the protection code. It's transferring it to X. It's then doing a JSR to C3CC, and if we have a look at C3CC, it's doing a whole bunch of TXA, EOR, store. Well, that's an obvious descramble. It's actually incrementing the border color on every single byte as well. So we're going to get a very messy screen of updated border colors. So this is the memory block before, and there's the memory block after. It looks a lot different. We can actually see what looks like code now at 1000 in hex in the C64's memory. We can definitely see a bunch of code now. 17FC shows that there is code there. Definitely looks a lot more sensible now. We can see that there's a JSR to 1000 in hex at C3, C9 on the Commodore 64's memory. I'm pretty sure that it only executes the code from this point at 1000 once. Basically, it only executes that JSR 1000 in hex once. Pretty sure. I don't think it gets back to this code. Why would you want it to get back to code which pulls the value from the stack and then descrambles? I don't think so. Well, actually, it just descrambles with whatever is in X, which doesn't make much sense, does it? No. There we go. So it's finished the descramble. We know that this is the code that has come from the loader. Pretty sure it doesn't actually ever get back to there again. We can see it's doing a bunch of loads before it gets to the title screen. It does a bunch of loads on the black screen. Again, I never like a black screen when something is loading. Yes, the drive makes a whole bunch of noise, but still, a black screen while loading is never really good. A long black screen while doing anything is not really any good. Calculation or loading, regardless. Black screen is not good for a user perspective. They think the game's crashed, right? When, a long time ago, when I was doing console game work, there would often, but not always, be technical requirements that said, you shall not have a blank screen longer than X amount of time. If it's longer than that, you have to have a message on the screen. Otherwise, the user thinks the game's crashed and will press the reset button. So I was just checking that, yes, actually, we're running a whole bunch of extra drive code now. After the breakpoint is hit for getting into the descrambled game code, it does extra loading, again, with more drive code. Fantastic. Again, it's using a 2-bit protocol, but here we can see that the routine looks a little bit different. We can see that there's some no op gaps here for this routine, but the routine after it doesn't have no op gaps. So the first routine for the 2-bit protocol is B41 in hex in the C64's memory, and the second one is B5E, and there aren't any NOPs between the load and the next load X, and the OR A and the next load X. We can see, because this is the PAL version, we can see at this particular point in time that this is the RTS which is hit here. It does a clear interrupt and it immediately goes into running the interrupt handler on the C64. Great. B19 in the Commodore 64's memory, the code there looks like it's definitely getting a byte. The routine at C99, or rather C99, the JSR, definitely seems to be getting a load address and storing it into AE and AF in the 0 page. It is doing that escape code check by comparing it with 1 all the time. Again, it seems to be storing memory now, or loading memory into 4000, which is the address that we get from AE and AF. So the escape code basically seems to indicate when the end of the file occurs, because you can see there's a compare and branch on equal C24 and C26, and it basically says that that's the end of the file, and then it jumps over the store, the increment y, etc, etc, right? So that's obviously why there I would have transmitted the file length, for example. However, if you need to transmit the file length, of course you need to transmit, or you need to calculate that or store that somewhere in the drive. There's extra complexity there. So there are pros and cons with having a control code. It's a little bit less efficient, but it's easier to code because you don't have to maintain a directory listing or anything like that. So anyway, the data which is read now, stored into memory on the Commodore 64, it seems to load more than one chunk of data. So if I'm going to properly hack the game at this particular point in time, I would investigate this data load routine in more detail, because I know that Flying Shark is a multi-load game. However, at this point, because I'm just wanting to create a compressed copy which I can load and run quickly, as opposed to going through all of the loading of the data and everything like that, then I might just save it after this load has completed, and then save the memory and then compress that. We'll see. I don't really want to extract all of the individual data chunks and then rewrite the disk loading routine. Right. Although, yeah, I don't really want to do that. That would take more time. So C52 with the RTS, that seems to be the end of the load data chunk routine. Look, it does a kernel init IO as well. This is intriguing. It seems that the 2-bit protocol routine is reinitialized every time it wants to load some data. Well, that's certainly easier. If there's no extra protection checks at this point in time, then it would certainly be easier to copy the disk, without protection, and run a compressed version of the game at this particular point in time at the code. So when it was running from 1000 in hex onwards, we could take a snapshot of the memory at that particular point in time and then compress that and then run that. But then we would need a disk with the data in the tracks and sectors in the same places that the game is expecting them to be in, which we could certainly manage. That would be okay. However, to kind of properly, in inverted commas, hack this game, it would be nice to make it a completely DOS format disk, wouldn't it? So you would want to have each data file as a separate directory entry. It means that you would discard the 2-bit protocol that's being used here. You might add in your own 2-bit protocol, but theoretically you could do that too. You could just replace it with kernel load. You could do a set name, a set LFS load routine, and then remove all of this 2-bit protocol loading code. You could do that because it doesn't seem to have this screen enabled Doesn't have any raster bar effects or any music playing or anything like that between the levels, right? So could certainly do something like that too. But yeah, this game does a lot of initialization of code into the drive's memory and runs that code. An awful lot. Does it very often. You know, technically if I was doing this, I would probably send or load the drive code once, maybe twice. It would speed up the level data load, I'm assuming is the level data, if the interrupts were not enabled, because it would mean that the Commodore 64 is not servicing the standard kernel IRQs, so it would speed up the 2-bit protocol load a bit, because the time would not be taken, the CPU time would not be taken up with processing IRQs. So I would have left the interrupts disabled at this particular point in time, especially since the standard IRQ doesn't seem to be doing anything. It doesn't seem to be having any traps inside the vector table. Don't forget that the code restored the default vector tables just before getting to this point in time. So we have that init IO, kernel init IO again. And yeah, C52, definitely the end of the load data chunk. Then we have a C increment of 3CD6. 3CD6 seems to be the file number? Maybe the last file that was loaded, perhaps? Maybe it does that so it knows which file to load next when it's loading the next level. This does an RTS, of course. So after the close all, or clear all, whatever it is, I think it's close, right? Oh look, it gets back to 180D because it's pulled that from the stack. So I'm kind of guessing here, but maybe 17FC load 1, store it in 107 is basically saying, I want to start loading level 1 data, or level 1 data files, or I want to start loading file number 1, perhaps, something like that. And then it goes off and does the JSRs for the drive code initialization, maybe the load routine, and then it comes back and then stores it, and then 180D seems to be the return point, where it does some extra stores and things like that and sets up the rest of the game data and blah 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 and starts running the title screen code. Perhaps. Just guessing, but that looks like the kind of structure that's there. So maybe 180D would be the point in time where we want to basically save all of the memory and then compress it and then run it from that particular point at 180D. So we're going to put a breakpoint there. We are going to reset. Then we're going to load the game again. I'm going to execute all the way up until that point. And yes, breakpoint, good. Corrupted data. Why? I know why. It's because, does anyone remember why? I remember why. Quick quiz time. What did I do slightly wrong there? I forgot to set the monitor into RAM only mode, so it was saving all of the memory from the CPU visibility point of view, which was basically ROM and RAM mode if the register 01 on the Commodore 64 was set differently to what I was expecting than it was in RAM and ROM mode, so I saved ROM, which was a bit stupid. So I have to run through the whole thing again, breaking at 180D. Now I need to remember to set RAM mode this time. So here we are loading the game again. We'll wait until we get to that breakpoint after all of the loading data has finished, which is at 180D. We will then definitely set the memory mode to be the bank, the RAM bank mode, and we will save all of the data minus a little bit because I don't think that we need it. At the end of RAM, underneath the kernel, there's actually some IRQ tables and stuff like that, which I don't think that we need. Just want to double check that, don't I? This is a hard reset. This clears the memory. For loading, we also need to set the bank to be RAM, just to be on the safe side. That's the processor port register at 37, because we're after a reset, of course. And there we go, Go 180D results in the title screen being displayed with the game playing after you start the game. And everything seems to be okay. And that's after a cleared memory hard reset. So that seems to tell me that the memory that was saved is good. So let's compress that. Now I'm using my own compression tool here. So let's compress the file, but with the hex start address of 180D. Using the max border U mode for the compression, it enables memory from 200 in hex all the way up until the end of memory. It flashes the border, as you can see here, and then it starts executing the code. And there we go. And the only thing I can see here is that the characters on the runway are not correct. That's interesting. Maybe it's the data right at the end of memory in the RAM underneath the kernel. Unlikely. So let's try and fix the data at the when the game starts with the runway with those corrupted characters. I'm looking for a bit of spare memory. If you remember, when it was decompressing, most of it said it displayed loading flying shark in the screen memory with a little bit of used memory right up at the top, but mostly the rest of the screen memory seems to be empty. So what I'm going to do is that I'm going to save a new copy of all of the memory. Wow, how many more times am I going to make that typo and forget that I need to put 0 for the device? Okay, I just remembered that my compression tool doesn't compress the last few bytes because it's the IRQ table normally, and normally I don't need to compress the IRQ table because I normally initialize it. First, let's load the good data back again, if I can remember how to not make a typo. There we go. Getting tired, obviously. So yeah, I'm going to use that spare memory space as some backup and restore space. So I'm going to save the bytes in the RAM at the end of memory. So transferring from FFF8 to FFFF, I'm going to transfer those 8 bytes to 600 in hex, which is free memory. Well, it's filled with spaces. It looks like it's free. And then I'm going to assemble some code at 700, which will do the following. It will copy 7 bytes, index 0 to 7, basically, and it will load it from 600, and it will store it at FFF8 dex. There we go. And then I'm going to jump to 180D, and I'm going to save that as new memory. There we go, we can see the memory, right? The 8 bytes at 600, and the code that was assembled at 700. A207BD, blah, blah, blah. We can see that in the disassembly. I'm going to save it. I need to change the start address, the run address from hex. Yeah, no, that's wrong. I used decimal rather than hex. Saw it that time. There we go. So we can see now those 8 bytes and then the little code in the spare memory space, and the runway is still wrong. And that's because I'm an idiot and I forgot to change the processor port again. Which, to be honest, is probably the more important thing to do, right? The processor port, which also needs completely updating properly before doing the jump to 180D, which is actually the thing which is really fixing the characters on the runway. But for completeness sake, I'm going to leave the last 8 bytes restore in there anyway. So let's save that new data again. Let's recompress it. There we are. That's the one that we want. And then let's run it. And perfect, fine, great, fantastic, wonderful. The compressed version now works and the runway characters are all good. So yes, let's ship it. So anyway, now that we have a, in inverted commas, hacked version, we can use that to run the game. So we can just load the prog file now, PRG file, in the C64 debug GUI application. There we go. Loading, decompressing, run. Standard character screen mode for the title screen. I never noticed before, but the left-hand pixel of the upper and lower parts of the Firebird logo were white, not red. Anyway, so we can see here initially that Sprite 1 seems to be used for the score panel, and Sprite 1 is duplicated going all the way down the screen, and also Sprite 1 is expanded in Y and X. We can see that very clearly in the Vic debugger. We can see that the area underneath the score panel has those solid yellow characters and the solid green characters. So I'm guessing that there's a black, obviously there is a black expanded horizontally and vertically Sprite 1 containing the score and lives and smart bomb indicators, and actually the transparent colour is showing the character colour underneath, and the black colour is used to mask out the scrolling characters. So Sprite 1, not Sprite 0. Sprite 0 was being used, as far as I could tell, by the plane, the player airplane. Sprite 0 seems to be used all the time, at least initially anyway. Now the multiplexor in this is actually pretty good. One of the things that I noticed when playing this game, even back in the day, was that the multiplexor is actually pretty powerful. So we can see in the Vic debugger that if I move up and down with the screen position, we can see that Sprite 1 is consistently being used up and down the screen for the score panel. I'm going to pause it so we can inspect this in more detail. We can see that the sprite boundaries, because they're expanded, the score panels, the score information is actually aligned, and there's some black pixels in the top and bottom of each of those score sprites, and also the smart bomb and lives sprite. This gives more than enough time to move the sprite down and also update its definitions for the sprite frame that's being displayed. You see, if we turn off the sprites, we can clearly see those characters in the background. If we move up and down, we can see how the same Sprite 1 is being used. Sprite 0, definitely the plane, airplane, the player control plane. Now, if I move up and down, at which particular point does it update these sprite registers? Well, we can see that if we get to a point on the screen in the raster position, we can see there, look, there's a PLA, RTI, and just up above it, it is updating DD, 04, 05, 0E and 0D, DD is CIA2, which deals with non-maskable interrupts, and it looks like it's setting the timer value for the NMI. Just up above that, we can see it's doing an STA-D003, and it's then adding clear on carry, adding carry to A, and then storing it for the next value to use. And it's also incrementing 43F9 and 47F9, which are the sprite frame pointers. So we can definitely see that it's using a timed NMI. Definitely using a timed NMI. The NMI being a non-maskable interrupt, it is the highest priority interrupt, which even interrupts IRQ, even if they're running. So that's interesting. It's using a rolling NMI as it goes down the screen. So having black pixels above and below the score panel information, and those are black pixels which are not transparent, so it gives enough time. It gives like a line or two of wobble, if you like, to update the next sprite's position. Now, if you try and update the Y position that a sprite is being displayed at, that new Y position will not take effect, generally speaking, unless you do some really clever expanded sprite toggles. The Y position will not be used until the sprite has finished rendering. So you can update the Y position for the sprite quite safely in terms of for the next Y position to render, because the VIC won't pick it up until it's actually time to render that new. So you don't get gaps. The important thing here is that you don't get gaps even if you reuse the same sprite when you update its Y position. The only thing you really need to worry about is the sprite definition. But because every single sprite definition has the same colored pixels, in other words black pixels in this case, you can afford to wobble up or down a couple of raster lines when you're updating the sprite definition, because the top and bottom of the sprite frames are the same, so you're not going to get any problems there. They look identical, so it doesn't matter if the updates are a little bit early or a little bit late. So it's quite an efficient usage of one expanded sprite, X and Y expanded sprite, all the way down the screen to create this score panel. Even with the multiplexing going on, Sprite 0 always seems to be used for the airplane, and that also makes sense if you want to guarantee that the player sprite is always visible, and if you want to guarantee that the player sprite is always going to be over everything else in terms of priority, then you would probably reserve Sprite 0 as well. Generally speaking, I would not reserve the player sprite. I would allow the player sprite. I would allow all of the sprites to be used in the multiplexer, with the exception of the score panel sprite, of course. Because then it allows slightly more complex enemy and bullet information to be displayed in the sprite multiplexer, because you're giving it one extra sprite instead of reserving one sprite all the way down the screen. Interestingly, the player sprite never goes over the score panel. Even though the player sprite could go over the score panel if the player movement was unlocked. To be honest, if you wanted to, the game could have been coded so that Sprite 0 was always using the score panel and Sprite 1 was the player sprite, and then the player sprite could have gone underneath the score panel like all of the other enemy sprites. Because the enemy sprites are all using Sprite 2, 3, 4, 5, 6 and 7, they are a lower priority sprite, so they appear behind the score panel. I'm painting characters into the score panel sprites here, and you can definitely see that the transparent areas of the score panel sprites show through, and you can see that because I've added some transparent pixels where it transitions from yellow to green, it wobbles up and down. That's because the characters behind are scrolling up and down in 8 pixel steps. If I put characters here in the screen, you can see that it never scrolls this area of the screen. It never does a character scroll. It does a pixel level scroll because that's the hardware pixel level scroll, but it never does a character scroll in this area of the screen, and it doesn't have to. The entire right hand, the last 8 or 10 characters of the screen on the right hand side are never scrolled. It never updates them for the whole, for the whole level. So that's the C64 debugger, and that was showing us how the score panel sprites are laid out. Now I'm going to go back to ICU debugger for a little bit more memory debugging, because it's more comfortable to view large ranges of memory in this tool as opposed to the C64 debug UI. So let's have a look at some character screens and some text screen. Let's have a look at some text screens and also the sprites. So we can see even when the game is running, there's very little memory used in the default screen memory. It's added some clear values there and stuff like that, but I paused the game, it's not crashed you. If I leave the music playing, if I don't remove the audio, then you can hear the music in the background. Now it's interesting that the music loops for the intro section when you're in this part of the level, when it's paused. And the music syncs up with what's happening in the level as well, I've noticed that. So it plays different sections of music depending on where you are in the level. We can see that it's got a whole bunch of sprites. We can definitely see the score panel sprites there as the last sprites in the bank. We can see actually that the game has got some available sprites as those black and white lines in the last part of the sprite bank. Now in the character text screens, we can see that the two screens are double buffered screens for character screens, and we can see where the character set is. The character set is at 4800 and the screens are at 400 and 4400. So there are two of them, and they are narrow screens as you would normally expect. We can see that it updates each bank for the text screens across multiple frames. We can see the characters ripple down the screen. When the game comes on, when it's setting up the level, it does that very quick scroll in the background with the screen disabled. A normal trick, you don't want to generate more code than necessary. So it just does a very, very quick scroll to bring on the level. The interesting thing to note here is that at F000, all the way up in memory underneath the kernel, we seem to have a wide screen version of the map as it scrolls down. Let's run that again, and you can see, look, it's not aligned to the screen view. There seems to be an offset of 256 bytes, 100 bytes in hex. But yes, this definitely seems to be mostly, apart from maybe the last 1, 2, 3, 4 characters on the right hand side perhaps. Or maybe it's wider. No, it's not, it's the last 4 characters. Anyway, we can see that it's got a wide version of the... Oh, it's shifted by 4 characters. Okay, maybe 5 or 6 characters perhaps. Anyway, we've got a wide version of the map. If I update the characters in the wide version of the map, it then copies those updated characters in the wide version of the map that's being decompressed to the screen. You can see it in the double buffered screens, it's copying them over. We can see it in the game as it's running in the emulator. So that's an intriguing way of doing it. It basically calculates the wide version of the screen somewhere else, and then it progressively copies the narrower version into whatever double buffered screen bank it wants to render next. Quite an efficient way of doing it. It certainly means it means in this case that the game doesn't need to have an update block on the right position on the right hand side character column and the left hand side character column as it scrolls the screen left and right. It can just copy a range or copy a span of pixels horizontally across the screen for a narrow range from the wider decompressed map in memory. So that's pretty cool as well. That's a good way of doing the scroll. I like this UK version of Flying Shark because it has the aspect ratio which kind of matches the aspect ratio used in the arcade game. I mean, I appreciate the work that goes into multiplexing the score panel expanded sprites. We can see, actually, that it's doing a whole... Well, okay, so that's doing a whole bunch of copies. So the character set is here. We have some animated characters. So the water characters, for example, are animated. We can see that in the character set view here. We can see the animated characters for the water. They're scrolling down right now as the game, even if there's no water visible, it's still scrolling the water characters, which is okay, it's fine. It's guaranteed frame execution time. You might as well just scroll them, I suppose. I probably wouldn't. I would probably scroll them only if there was really water visible on the screen, but hey ho, never mind. Now, when I was very young, and when I remember maybe once or twice when I was playing this game, that occasionally if I died in a really weird place, the characters were changed. So palm trees would be displayed as explosions, or parts of buildings, and I thought that was really weird. So I think that sometimes the character set data is being updated as the game scrolls through the level. Not part of the normal, inter-level data load. It's actually during the level, as it's scrolling down, it seems to, I think, update some of the characters. Now, we've seen games update characters before, like Power Drift, like Turbocharge. They do that to generate more graphical variety, and I'm not surprised that this game also does that, because this game has, pretty nice background graphics and pretty varied, so there should be some updates. Now, we can see here that I've died and it's reinitializing the characters, but it's copying the characters from somewhere and storing them into the character set data. This is not part of the animated character update. This is actually updating the first few characters, which, as you can see, are not scrolling. So, my feeling here is that, okay, so I'm terrible at the game. I cannot get far enough through the level to trigger the subsequent character update, which is a real pain. If anyone knows a good cheat code for turning off the collision detection with the player, let me know. Please post it in the comments below, and I might produce an updated video to show the updated character set during the level. But I think I need a cheat code to turn off the player collision, basically. I am really rubbish at, and I'm trying to watch the character set data as well for being updated at the same time as playing, and I can't. It's very, very difficult. I don't have 4 sets of eyes. I'm listening to this game over music far too often now. It's going to go into an earworm in my brain, isn't it? So let's expand the rendered character set data a little bit to make it a little bit easier to see. There we go. Let's zoom in a bit. It's initializing the level data again. It's doing this copy again. It's also, if you notice, cleared the 2 screens, with the exception of the sprite. I think those are probably the sprite frame pointers, right? So we can see that it's copying characters from D000 to 4800. So if we look at the character set data and we look at the character set from D00, we can see that, oh look, there's a whole bunch of extra characters. Loads of them, actually. In fact, oodles. So yeah, this game definitely seems to be wanting to copy character set data from way up in memory all the way down to the character set which is being used during the game level. Which is a really good way of getting graphical variation into your game and making it look really nice. So I think we're going to leave this video here. It's gone on for long enough already, and I need to edit this and then send it to YouTube. So thank you very much for watching these game retro memories and technical deep dives into game code videos. If you like this kind of thing, then please do consider liking or subscribing to this channel, and there are buttons below specifically for that purpose, and it would be wicked great fantastic if you could press one or both of those buttons to like and subscribe this video. And also, if you want to, add a comment in the comments section below or ask me questions or anything else like that, that would be fantastic. So thank you very much for watching. Take care, have a great day wherever you are.